Okay, well, welcome class. Today we're in Unit 1, Activity 4 on limits of functions, and this may be a long lesson. Limits of functions and then 1.5 properties of limits requires a little bit of work here, and it's really a new concept that is one of the first ones that we see new in calculus and vectors. So this may take, like I said, this may be a little bit long. I may also break it into two video lessons. So let's get started on it. Um, we saw limits in the previous section when we did rate of change and the definition for an instantaneous rate of change, we took the limit of the slope, right? And the limit we did as h approaches 0 or as b approaches a, so just as that gap gets closer. So limits, the concept of a limit um, is really here in this first definition. Limit of a function is expressed with the word lim, so limit as x approaches a of a function, and it equals a capital L in this definition, and that capital L is a constant. Usually we talk about how we read it as the limit of f at x as x approaches a is equal to L. So as x is getting really close to a number, a limit by its definition is around or in the neighborhood of a value. So when you take the limit of a function, we're not actually evaluating the function, okay? Not necessarily, but we're looking at what's the value of that function around that limiting point here. So in this case, by our definition, if it's a, as x approaches a, we're looking for values of the function at really close values to f at a. And we'll work through a lot of examples here and go through that. Okay, so we're always talking about some key terms here. It's arbitrarily close to L. Okay, and the concept of a limit, like I said, we talked about it in instantaneous rate of change. Okay, and we often can find the value of a limit by straight substitution, especially if it's a continuous function here. Okay, so often we will solve limits and determine a value of a limit just by putting in a value. So here's the first example here. So if I'm asking you to find the value of this limit as x approaches 2, if you have the limit x squared minus 1, I know x squared minus 1 is a continuous function, right? It's a parabola. Okay, so I simply can just plug in my value here. So I can directly substitute x equals 2 into my function. I get a value of 3. Now, I'm going to take a break here at this point and go to my lesson here in this first lesson. Okay, focuses on this function here, this one was in the example. So when we did evaluate it at 2, right, that's right in here. Okay, this is f at 2. Okay, I get a value of 3. Okay, so here's the investigation in the textbook, and I'm going to walk you through this as our lesson here. Okay, so let's fill in the table. Okay, so f at 1. Okay, f at 1, I got that to be 0, and f at 3. If I put 3 in here, I'm going to have 3 squared is 9 minus 1 is 8. Now the other values I can get, okay, by directly substituting 1.5 would be next, 1.9, 1.99, 1.999, and I want to just focus on this right here, because that's what b is. As x approaches 2 from the left, starting at 1, what is the approximate value of y? So in b, when I say as x approaches 2 from the left, starting at 1, this is what I'm asking you to do. The limit as x approaches 2 from the left side, and that notation is a little negative sign, okay, in looking like an exponent. There's no number there though, it's just a 2, okay, from the left. Okay, so as I approach 2 from the left hand side, so those would be the values 1, 1.5, 1.9, 1.99, 1.999, and I want you to fill in these values here. So that's this function, and that's just what I'm asking you. And I take values, okay, they get really close to 2 from the left hand side. Okay, now I've done this work for you. Okay, so I've got 1.25 here, and I got 2.61. Notice that I'm getting really close to 3, right? getting really close to 3. Okay, and that's kind of a limiting value here, and that's how I would say that. Okay, in C, I'm asking you to do the other side, from the right side. Okay, and when I am to show that as written as a limit, as x approaches 2 from the right, okay, that would be as x approaches 2 from the positive side of the right side. And I would show that here. So I started at 3. Okay, I got a value of the function to be 8. 2.5 gives me 5.25 approximately. Now I rounded off a little bit, so it's not a big deal here. 2.1 gives me 3.41. 2.01 gives me 3.04. And then 2.001, I get even closer to 3. Okay, and that's kind of what I'm looking at here. Now, my apologies, okay, if you can't read that or see that. Okay, and that's just a straight substitution. So how did I get 2.1? I found f at 2.1, and I plugged the 2.1 value into this function here. Okay, so I also find, okay, now graph, okay, x squared minus 1. I don't have Desmos open, but I'm just going to do a quick graph. Okay, that's a parabola. Okay. Okay, at the point 0 and negative 1. So my function is x squared minus 1. Now my focus was on this point right here. Okay, so if this is 1, this is 2. My focus was right here. Okay, and I think I found that to be 3. So my focus was on the point 2 and 3. Okay, and what I found, okay, what I found was that as x approached 2 from the left-hand side, my function approached 3, and as x approached 2, that was this. Okay, that was from the left-hand side, so that was the limit as x approaches 2 from the left-hand side. Okay, I found it to be 3. And on the second part of it, okay, I found as x approaches 2 from the right-hand side. That was that one here. So that was the limit as x approaches 2 from the right-hand side of my function. And I found that to be 3 as well, too. So that's kind of what it looks like, and you see that using arrows illustrate. I just did E, illustrate that as we get closer to the value of x, it's closer and closer to 2. Value of y gets closer and closer to the value of 3, and explain why the limit, okay, exists at 2. Well, it exists because simply it's a continuous function. Okay? The limit exists because there's no breaks in it or there's no holes in it. Okay, and it doesn't become discontinuous here. It's a nice continuous function. Okay, and there's a value here. Okay, and that value, okay, equals the same no matter what side I approach it on. Okay, so as we get going through this section on limits, and this is an introductory work on limits here, these are going to be really important here. Okay, so if I approach the limit from the left, and I also approach it from the right, and they approach the same values, and that value also holds when I actually just evaluate the function at that point. Okay, now this concept, okay, I'm going to use the word converge, okay, or convergence. Okay, when the limit converges to, okay, the same value on either side, on the left-hand side or on the right-hand side. Okay, we're talking about the limit exists and why that, okay, why it exists when we do that kind of thing here. Okay, so here's our notation. Okay, a limit, and limits can either, okay, approach when you find the value of a function, you either have to look at it from the left-hand side. Okay, that's a left-hand side limit, or a right-hand side limit. You look at it from the right-hand side, and in each case, okay, we sort of do this same thing here. Okay, we do left-hand side, right-hand side convergence. Okay, here's left-hand side, here's right-hand side, and we look at the function and see what its, okay, what its limiting value is going to be. So all these are new terms here. So we read it as the limit of f at x as x approaches a equals L, it means that the value of the function can be made arbitrarily close to L by choosing x sufficiently close to a, but not necessarily equal to a. We're looking at, okay, we often use the word, okay, around, okay, or neighborhood is used in this course, the neighborhood. And I think you guys know the concept of a neighborhood, right? What's happening around, okay, the point, right? What's the value of the function around the point? Okay, make sure that we can always take a look at any point on our function from the left-hand side, okay, or from the right-hand side. Okay, and if that's our function, okay, that's the kind of the way we, okay, see this. And this left-hand side, right-hand side thing looks familiar, right? Trig identities. We're looking for balanced equations here, and we're looking for converging, where functions on both sides of the equation sign equal one another. Okay, we can find values of functions by graphing. I'm going to pause this and go into Desmos, okay, and sort of see this. But before I do that, okay, I want to take a look at this particular function. That's the function I'm trying to find here. Okay, x squared minus 1 over top of x minus 1. Well, it looks like, and I'm asked to find the limit as x approaches 1. Well, what happens when I directly substitute? Let's just, before I graph it, let's directly substitute. What happens when I, okay, do this? And I've got, okay, and I put this right in here. I put 0 over 0, okay? That's a common 0. We talked about that in the first section here, common 0. Okay, and that's a problem, right? This doesn't have a value. There's no value here when I direct substitute, okay, f of 1 into this limit. Okay, what do I know about this function? Okay, I'm going to graph it here in a second, but what do I know about that function? Well, I get Desmos set up, okay? You guys think about that function. You've seen that function before. Okay, here's my function. Okay, it's a straight line when I graph it. Well, it's a straight line. I kind of thought it was a rational expression though, right? X squared minus 1 all over x minus 1. But the graph shows me something different. The graph shows me a straight line. Wow. I don't know. Okay, I think maybe there's been, okay, some sort of division on this, or okay, certainly been simplified. So we're going to simplify here in a minute. And I want to determine the function by graphing. So I have to zoom in. What was my question? I was asked to find out when x equals 1 here. I'm just going to adjust this. Okay, I'm going to zoom in. Okay, so x equals 1. Okay, so let's approach it from the left-hand side. Okay, x approaches, okay, and then let's approach it from the right-hand side. It sure looks like my function is approaching 2, right? Okay, what happened here? Look at when x equals 1. There's that undefined, right? At x equals 1, the actual function, okay, because the denominator is 0, right? 1 minus 1 is 0, okay? So it looks like I've got a hole here in my graph here, that open circle hole, okay, is an undefined point. But the limit is asking it for a different thing. It's not asking for the value of the function at 1. It's asking for what is it around, okay, around 1. Okay, so either from the left-hand side, okay, or from the right-hand side. It looks like the value of the function, okay, is 2. Let me minimize this. Okay, and, okay, so my question was, and I found it to be 2. Okay, and that was from Desmos. Okay, because that's around. Okay, this was around. What is f1 around the point? Okay, x equals 1. Okay, and that's what I wanted to find out. Well, I could have did this, and I want to show you how to actually do this and get that answer algebraically here. Okay, so here's what I could have done. Because I don't always have the ability to graph a function, okay, and read from it. Okay, well, I can simplify it by factoring. Okay, I can factor the top. Notice it's the top is a difference of squares. Okay, and then, okay, I can simplify. substitute. Okay, so I can get a value of a limit, okay, by simplifying my function. I can do that by simplifying that. Okay, and that's just what I did here. That's exactly what I do that. Okay, so let's move on here. Okay, determine it by tables. Okay, well, I think we know what the value is. Okay, so I simply have just I gotta put in my pen tool here. There we go. Okay, so from using a table, okay, I'd have values as x approaches 1 from the left. I've had values as x approaches 1 from the right. Notice that they're approaching 2. That's what we found on Desmos. That's what we found algebraically. And with the table, I'd find that same thing. Keep in mind, though, that the value at the function, the value of the function at 1 is undefined. But as it's approaching 1 or getting close to 1 from either the left-hand side or the right-hand side, the limit is approaching 2. Okay, next up is a piecewise function. And again, you may know a little bit about piecewise functions. We've started to see them in some of the homework questions. Okay, and you may have been introduced to them in advanced functions. So a piecewise function is a function that's in pieces. And there's always a breakpoint, or more than one breakpoint. In this case, the breakpoint is x equals 0. So, this is from the left-hand side, and this is from the right-hand side. And again, that's the inequality. So this inequality, when it's less than or equal to, it's from the left-hand side. So when I approach 0 from the left-hand side, I have to use this function. Okay. Now this function is a parabola that opens down, and it has a point. So when x equals 0, I've got a point at 1. I'm going to graph this in red, and I open down. And it includes the 0, so that's a solid dot here. Okay, now I'm going to change my colors here. I'm gonna let me erase. I'm just gonna erase this color right here. Okay, and let's go to purple. Okay, and now this one here is from the right-hand side, and that's because when it's greater than, and I have to follow the function square root of x plus 1, so that's at 0 then, so I'm going to use my value at 0, but it's going to be all at the right here. So the square root, when x equals 1, using the square root of x plus 1 function, I'm going to have 0 plus 1 is 1, and then 1. So this point here, I follow the square root sign, so the function, the square root function, kind of looks like this. I have a point here at 0 and 1. That's going to be an open circle because it's greater than. And I need another point. Let's use 2. Let's use 1. I'd have root 2. So that'd be about here. At 2, I'd have root 3. That'd be about here. And when x equals 3, I'd have the value of 2. So it grows. But that in the purple is an open circle. So I want to find the limit of my function as x approaches 0. So what I have to do here, is a couple of things here. I'm going to first, determine the limit, okay, of the function, okay, as x approaches 0 from the left-hand side, okay, and from the left-hand side, okay, was this function right here, okay. I have to evaluate it, okay, and I think I did, so I can plug in, okay, so I can plug in 0, okay, into my x squared function, right, and I get that to be 1, okay. So that's because this left-hand side, that's the function I have to use. It's on the left-hand side of my breakpoint here. On the right-hand side, I use the other function. Okay, so I use this function here. Better check and see what it was. X plus 1. Okay, and that's still 1. Okay, and that's has evidence paired in here. Okay, so they do converge along the same point. They come at it from different functions, different directions, okay? And when I have this convergent, okay, when I have from the left-hand side equaling a certain constant, from the right-hand side equaling a certain constant, I can then determine, okay, if these are the same values, I can determine this, okay? That my limit, no matter which side I approach it on, exists, and it happens to be 1. Now further, I can find the value of the function at 0, the actual value of the function at 0. But in order to do this, I would have to use, okay, this function right here. Okay, so that's kind of, okay, this was my answer to my question. Okay, but make sure we understand the difference between using either function. Okay, here's a big piecewise function. Okay, we've got a variety of, okay, we have things here for this piecewise function. Okay, it looks like our breakpoint is, okay, at 1. Okay, so I've got below 1, right? So from the left-hand side, okay, below 1, that's everything from this point, okay, that's this point on. Looks like I follow a straight line, x minus 1. Well, straight line x minus 1, okay, would look like this, an intercept of -1 and a slope of 1. Okay, so I go all the way up to here. Now, does it include 1? No, it does not. It's okay, so that has to be an open circle here. I'm going to try and draw that a little bit better. Okay, so that's part of my function. That's this part. Okay, so I got this one. Okay, so at 1, at x, okay, so right at x equals 1 here, I have a value of 1. Okay, so at 1, I've got this value right here. That's a solid circle. It's just a point. Okay, got that one. Okay, and then it changes. Okay, so when it's greater than 1, okay, so when it's greater than 1, I have this new function. I've got a square root function, and it's been shifted. Okay, it's focal point here. So let's get a value at 1. Okay, so what's happening, okay, at 1 here. So along this line, x equals 1, but I'm going to focus, I'm going to get a value, a starting point, but focus that way, right? So focus on that way. So at x equals 1, I'm going to put in 1 minus 1 is 0. Square root of 0 is 0 plus 2. Okay, so there's my starting point. Okay, now can I figure out when it's at 2? When x equals 2? When x equals 2, 2 minus 1 is 1. Square root of 1 is 1. Plus 2 is 3. Okay, so at point 1, 2, 1, 2, 3, it's up here. Okay, and I think I would continue to follow it along this square root function. So it's typically just a square root function that's been shifted 1 unit, okay, to the right and 2 units up. And there's my function. And this particular one was on the right side. Okay, so that function here. And this was at x equals 1. Okay, so what is the limit of the function at 1? Okay, well I've got, okay, what's the value of the function as x approaches 1 from the left? Okay, so that was 0. We found that to be 0. That's this right in here. It's the value of the function as x approaches 1 from the right. Okay, that looks like it's 2. Okay, I also found this. That's just the value of the function at 1. That's 1. look at all the three different things. Okay, from the left-hand side it approaches 0, from the right-hand side it approaches 2, and at the function it has a value of 1. So does the limit of the function as x approaches 1, what's the value of that? Okay, well, we don't have convergence, do we, here? Okay, from the left-hand side, okay, from the right-hand side, and even at the function. Okay, so this limit does not exist. Okay, and that's because we don't have equality or convergence. Okay, that's how we deal with that and write that. Okay, so in summary, limits in their existence. The left-hand side has to equal the right-hand side in order for the limit to exist. Okay, and sometimes they're not defined. Okay, they can have situations where they don't exist if you don't have convergence. Okay, and all these other situations apply here. So you guys have got some homework questions. Now I've added a couple of questions here. So you might have to go to your textbook PDF. Okay, I added question number 2. Okay, I added question number 12 and 14 and 15 as well. So I think those are important, okay, that we do all those. And I think it's going to take you a long time, okay, but certainly I want to make sure you're okay with some of these